What if two universes existed side by side? What would actually lie between them? Tonight, we'll journey through cosmic geometry, quantum theory, false vacuum, and hidden dimensions to uncover the most honest answer science can offer. Before we begin, tell us in the comments what you think might exist between two universes and where you're listening from tonight. If you enjoy calm space journeys, please like and subscribe. Before we can ask what sits directly between two universes, we have to slow down and notice the hidden assumption inside the question. Because the word between sounds simple, only when the objects being compared already share the same space, the same geometry, and the same system of distance. Two stones can have a patch of ground between them, two stars can have interstellar plasma between them, and two galaxies can be separated by millions of light years of expanding space. But a universe is not automatically an object placed inside a larger room. And if we imagine it that way too quickly, we may build the answer into the picture before the physics has even begun. On a quiet night, the sky encourages this mistake. It looks like a dark container filled with luminous things, as though space were an enormous black hole, and the universe were everything scattered inside it. Yet modern cosmology uses the word universe in several distinct ways, and each meaning changes what the title question is actually asking. The most immediate meaning is the observable universe, the region from which signals have had enough time to reach us since the hot early phase of cosmic history. Its boundary is not a wall, a shell, or a final surface where reality ends. It is a horizon created by the finite age of the cosmos, the finite speed of light, and the changing scale of space itself. Light has been traveling toward us for roughly 13.8 billion years, but because space expanded while that light was in motion, the matter emitting the most ancient signals we now receive is presently much farther away than 13.8 billion light years, giving the observable region a present co-moving radius of about 46 billion light years. That number describes our causal reach, not the size of all existence. An observer in a distant galaxy would possess a different observable universe centered on that observer, overlapping ours in some regions and extending beyond it in others, just as two lanterns in a fog illuminate different but partly shared volumes. If those two observable regions are casually called two universes, then what lies between them is no mystery at all: ordinary cosmic space, filled sparsely with matter, radiation, fields, and the geometry of the same larger space-time. They are not separate universes in the strongest sense. They are different windows cut by causality into one underlying cosmos. The second meaning is the universe as the entire connected space-time described by our cosmological model, including regions forever beyond our present horizon. Here the language becomes more demanding, because in general relativity, space-time is not merely a stage on which matter performs. It is a dynamical structure whose geometry responds to energy and momentum, summarized compactly by Einstein's field equation, in which the curvature represented on one side is related to the stress-energy content represented on the other. The equation does not require space-time to sit inside a pre-existing emptiness. It gives us an intrinsic geometry. Clocks, rulers, light rays, free-falling paths, causal order, volume, and curvature can all be defined from within the space-time itself. This was a profound departure from the older Newtonian picture of absolute space, an invisible and unchanging arena presumed to exist independently of the bodies moving through it. Einstein's theory replaced that rigid arena with a geometry capable of bending, expanding, carrying waves, and developing horizons, while the solutions found by Alexander Friedmann and later developed by Georges Lemaitre showed that a homogeneous and isotropic cosmos could evolve rather than remain eternally fixed. In the large-scale models now used in cosmology, the expansion is encoded in a scale factor, often written as A of t, which tells us how distances between freely moving, widely separated locations change with cosmic time. The familiar Hubble relation emerges from this geometry. The greater the large-scale separation, the greater the recession rate produced by expansion, although nearby gravitationally bound systems need not expand with the cosmic flow. None of this implies that the universe is swelling into an external void. The scale factor measures relationships among locations inside the spatial geometry. It does not measure the radius of a material balloon growing into a surrounding chamber. A two-dimensional analogy can help if it is handled gently. Creatures confined to the surface of a sphere could discover that their world is curved by drawing triangles, following geodesics, and comparing circumference with radius, even if they had no access to the third dimension in which we visualize the sphere. Their measurements would reveal intrinsic curvature. Yet our use of an external viewpoint to picture the sphere does not prove that every curved space must physically inhabit a higher dimensional environment. Mathematics allows a geometry to be described intrinsically, and general relativity normally treats spacetime in precisely that way. So if the word universe means one complete spacetime, asking what lies outside it may be like asking what point lies 1 kilometer north of the North Pole. The grammar survives, but the coordinate concept may have reached the end of its domain. The third meaning appears in speculative but mathematically serious models, where a universe is not the whole structure, but one region within something larger. In eternal inflation scenarios, for example, a universe may refer to a bubble-like domain in which inflation has ended and a hot cosmological history can begin, while other regions remain in a higher energy inflating state. Under that definition, two universes may indeed belong to a shared background, and something physical could lie between them, such as an inflating vacuum, a transition region, or a domain wall. But notice how the answer became possible only because the definition changed. The bubbles are called universes because they may develop distinct causal histories, perhaps even different low-energy properties, yet they are still embedded in a broader mathematical spacetime supplied by the model. The fourth meaning arises in brane cosmology, where our observable world could be represented as a lower dimensional surface within a higher dimensional bulk. If another brane carried another cosmos, then the phrase between two universes might refer to separation through an additional dimension. Again, the word between works only because the theory provides a common geometry and a metric capable of assigning a distance across the bulk. Without that shared structure, there is no physical ruler to lay from one cosmos to the other. The fifth meaning is more abstract still. In quantum cosmology and in interpretations sometimes described through branching worlds, universes may refer to decohered components of a quantum state rather than enormous spheres occupying different addresses. Such branches are not necessarily separated by kilometers, darkness, or an intervening substance. Their distinction is expressed through the structure of quantum states, correlations, and the diminishing possibility of interference. To ask what occupies the midpoint between them may confuse distance in ordinary space with separation in a mathematical state space, much as the difference between two melodies cannot be located halfway across a room. These meanings should not be casually blended. An observable region, a connected spacetime, an inflationary bubble, a brane, and a quantum branch are not five names for the same object. They answer different theoretical questions, rely on different mathematical structures, and carry different standards of evidence. The observable universe and the large-scale expansion of our spacetime are parts of well-tested cosmology, while bubble universes, higher dimensional branes, and ontologically separate quantum worlds remain model-dependent possibilities whose physical status is still debated. This distinction is not a weakness in science. It is the discipline that prevents imagination from disguising itself as discovery. It also gives us the first precise answer to the title. For anything to lie between two entities, those entities must belong to some common relational framework. There must be a set of possible locations, a geometry that defines separation, and usually a continuous path, even if that path is inaccessible or causally forbidden. In relativity, distance is not a free-floating concept. It is calculated from a metric, the mathematical object that determines intervals between neighboring events and distinguishes time-like, light-like, and space-like relationships. If two proposed universes possess a shared metric, then a region, boundary, field, or higher dimensional interval may meaningfully separate them. If they are disconnected parts of a larger manifold, they may share a theory without sharing any traversable route. If they are entirely independent spacetimes with no encompassing geometry, then their distance is not merely enormous and not even infinite. It is undefined, because infinity is still a value inside a system where distance exists. This is the quiet conceptual threshold on which the whole journey rests. Two realities can be distinct without standing side by side. They can both be described without occupying neighboring positions. They can exist within one theory while lacking any common place in which a midpoint could be found. And so, before we search for a membrane, a vacuum, a hidden dimension, or some unimaginably thin boundary between universes, we must first ask what kind of universes they are, because the deepest answer may not be a substance waiting in the dark. It may be that the darkness, the distance, and even the word between belong only to the geometry inside each universe, while beyond that geometry there is not an empty location, but no location at all. It is almost impossible to imagine a universe without quietly placing it inside something larger, because every object we have ever touched has been surrounded by other things. A stone rests in a field, a planet moves through space, a cloud drifts beneath the sky, and even the largest galaxy we can picture seems to float within a wider darkness, so the mind naturally takes one more step and asks what darkness surrounds the universe itself. Yet that final step may carry an assumption that modern geometry does not require. A universe, in the language of general relativity, need not be a gigantic object occupying a location in a greater container. It may instead be the complete system of locations, durations, paths, and causal relationships available within its own space-time. To see why this is more than a play on words, imagine an intelligent civilization living on an enormous two-dimensional surface, unable to rise above it or look down upon it from elsewhere. Its astronomers send beams of light across their world, survey triangles large enough to span continents, and discover that the angles of those triangles do not add to the value expected on a flat plane. They measure circles and find that circumference is not always equal to 2 pi times radius. From such experiments alone, without ever observing an external dimension, they can determine that their world possesses intrinsic curvature. Carl Friedrich Gauss established the mathematical heart of this idea in the 19th century. Curvature can be encoded in measurements made entirely within a surface, independent of how that surface happens to be embedded in a higher dimensional space. Bernhard Riemann then extended the language of curvature beyond ordinary surfaces, allowing spaces of 3, 4, or more dimensions to carry geometry as an internal property, rather than as a shape seen from outside. When Einstein built general relativity in the early 20th century, this inherited mathematical language became physical. Gravity ceased to be described merely as a force reaching across a fixed stage and became, in the theory's geometric interpretation, a manifestation of space-time curvature, with matter and energy influencing the metric, and the metric governing the natural motion of matter and light. The metric is not a material sheet hidden beneath the stars. It is the mathematical structure that tells a clock how much proper time passes along a path, tells a ruler how spatial intervals are measured, and tells a light ray which routes through space-time are possible. Once geometry is defined in this intrinsic way, an external viewing platform adds no necessary information to the local physics. A small creature on a curved surface does not need to know how the surface appears from above in order to predict the path of a freely moving object, and an observer in a relativistic universe does not need coordinates belonging to an imagined outer arena in order to describe planetary orbits, gravitational lensing, black holes, cosmic expansion, or gravitational waves. This distinction between intrinsic geometry and extrinsic embedding is the first reason the universe does not need an outside. An embedding can sometimes be mathematically useful, much as a curved map can be pictured as a sheet bent through three-dimensional space, but usefulness is not evidence that the surrounding dimension is physically real. Some geometric spaces can be embedded in higher dimensional spaces under appropriate conditions, and certain speculative theories do treat our spacetime as part of a larger dimensional structure, but general relativity itself does not demand such a container. Its equations operate on a spacetime manifold equipped with a metric, and the manifold can be studied from within, using relationships among events rather than distances from some external center. This becomes especially important in cosmology, where familiar pictures can mislead with almost perfect elegance. A closed, expanding universe is often illustrated as the surface of an inflating balloon, with galaxies drawn as dots carried apart as the rubber stretches. The picture captures one feature beautifully. Every dot can see other distant dots receding without any dot being the central point of expansion on the surface. But the air inside the balloon, the room around it, and the radial direction away from the surface belong to the analogy, not automatically to the universe. A three-dimensional cosmos with positive spatial curvature can, in principle, be finite without possessing an edge, just as the two-dimensional surface of a sphere has finite area but offers no boundary where a traveler falls off. Traveling continuously in one direction on such a surface could eventually return the traveler to the starting point, although the actual global topology of our universe remains observationally uncertain, and positive curvature is only one geometrical possibility. A spatially flat universe can also be finite if its topology identifies distant regions in a multiply connected pattern, while a negatively curved universe may be finite or infinite depending on its global construction. Curvature describes local geometric behavior. Topology describes the large-scale connectedness and overall identification of points, and Einstein's field equations do not by themselves select a unique global topology. None of these possibilities requires a physical wall beyond which a second kind of space begins. They show instead that finite does not mean bounded, and unbounded does not necessarily mean infinite, distinctions that ordinary experience rarely asks us to make. The idea of cosmic expansion is similarly easy to misread. In the standard homogeneous and isotropic description, the changing separation of widely spaced co-moving locations is encoded by the scale factor in the Friedmann-Lemaitre-Robertson-Walker metric. When the scale factor grows, the large-scale spatial distance between such locations grows. But the equations do not say that a cosmic substance is pushing outward through pre-existing emptiness. Expansion is a change in the metric relationships within space. There is no required outer rim racing into a vacant frontier, no unique central explosion point from which all galaxies were thrown, and no privileged direction pointing away from the universe as a whole. The hot Big Bang model describes an earlier state in which the observable cosmos was denser and hotter, not a conventional detonation occurring at one location inside an already completed room. Every sufficiently large region participated in the expansion, which is why distant galaxies appear to recede in a pattern broadly consistent with the same large-scale law from any typical co-moving vantage point. Even the phrase, "the size of the universe," therefore, requires care. Cosmologists can estimate the size of the observable region, constrain spatial curvature, and search for repeated patterns that might reveal a compact topology. Yet the total spatial extent may be vastly larger than our horizon, or may be infinite, and current observations do not give us a final global map. Still, whether the whole spatial section is finite or infinite does not force it to have an exterior. An infinite Euclidean plane needs no surrounding plane in order for its internal geometry to make sense, while a finite spherical surface needs no accessible edge. The deeper point is that existence in physics is not always the same as occupation of a position in a larger space. Spacetime may be the relational framework within which position itself becomes meaningful. Asking where the entire framework is located can resemble asking what time appears on a clock outside all time, or which page contains the book that includes every page in the system being defined. The question may be meaningful only after a larger theory supplies additional structure. Some research programs do exactly that. Brane world models allow an observable universe to behave like a lower dimensional brane within a higher dimensional bulk. String-inspired constructions can include compact additional dimensions. Quantum gravity proposals sometimes treat classical spacetime as emergent from more fundamental degrees of freedom. In those settings, a form of outside may acquire mathematical and perhaps physical meaning, but it is not the old empty box imagined by intuition, and no such framework has yet been established as the unique description of nature. The responsible conclusion is therefore not that an outside has been disproved in every conceivable theory, but that known cosmological physics does not require one, while any proposed exterior must be specified by additional equations, fields, dimensions, and testable consequences. Without those additions, outside the universe is not a mysterious region whose contents have merely escaped our telescopes. It may be an undefined phrase, because telescopes point along directions within spacetime, clocks measure intervals within spacetime, and distance is calculated from the metric of spacetime. If two independent universes had no shared manifold, no common metric, and no higher dimensional background linking them, then they would not be separated by an ocean of blackness. Blackness is already a visual condition inside a world where light and observers exist. Nor would they be infinitely far apart, because infinity is still a distance assigned within a geometry. Their separation would have no spatial value at all. There would be no line joining them, no midpoint waiting in silence, and no external observer able to turn and see one universe on the left and the other on the right. This is why the universe may not need an outside. Not because physics has discovered an impenetrable shell at the edge of reality, but because the geometry of reality can be complete without being placed anywhere else. And as that thought settles gently into the darkness, the title question grows more precise. Because before anything can sit between two universes, some deeper structure must first make them neighbors. When we picture the space between worlds, we often imagine a perfect darkness emptied of every particle, every sound, every trace of matter, as though reality had been erased and only a silent black interval remained. Yet the deeper physics looks into emptiness, the less empty it becomes, because even the most desolate region of the cosmos is not simply nothing. It is a physical state with geometry, fields, measurable properties, and rules that continue to operate long after ordinary matter has thinned almost beyond detection. The distinction begins with a simple historical change in perspective. In classical mechanics, empty space was often treated as an unmoving container, an absolute stage that could remain in place whether or not any object occupied it. Light complicated that picture during the 19th century, when physicists tried to imagine an invisible medium called the luminiferous ether, carrying electromagnetic waves in the way air carries sound. But increasingly precise experiments failed to reveal the motion through such a medium, and Einstein's special relativity removed the need for a preferred ether altogether. Empty space was no longer required to be filled with a mechanical substance defining absolute rest, yet it did not become meaningless. It retained the structure of spacetime, the invariant speed of light, and the causal geometry that determines which events can influence one another. General relativity deepened the transformation by allowing a region containing no matter to possess curvature, horizons, and gravitational waves. The vacuum Einstein equations do not say that spacetime disappears when the stress energy of ordinary matter vanishes. They say that the geometry must satisfy a particular condition, and that condition admits surprisingly rich solutions. The exterior spacetime around an isolated spherical mass can be vacuum, even though its geometry records the gravitational influence of the mass. A gravitational wave can pass through a region almost entirely free of particles, while carrying energy through changing curvature. A black hole's surrounding exterior can be described as vacuum, even while its causal structure contains an event horizon. Thus, classical emptiness already has more content than the word nothing suggests. It possesses intervals, directions, light cones, curvature, and the possibility of motion. If two cosmic regions were separated by such a vacuum, the space between them would not be an absence of physics, but a place where physics remained fully defined. Quantum theory makes the difference still more profound. In quantum field theory, the fundamental entities are not little particles drifting through an otherwise featureless void. They are fields extending throughout space, with particles appearing as quantized excitations of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field, and other known particles correspond to other quantum fields. Removing all detectable particles therefore does not remove the fields themselves. It leaves them in their lowest available energy state, which is what physicists mean by the quantum vacuum. This vacuum is not a turbulent ocean of tiny particles constantly appearing and disappearing in the literal, cinematic sense often used in popular explanations. That image can be suggestive, but it easily becomes misleading. Virtual particles are elements of perturbative calculations, rather than directly observed microscopic objects, briefly borrowing energy from nowhere, and the uncertainty principle does not grant nature permission to violate energy conservation for short periods. The more precise statement is that quantum fields cannot generally possess both an exactly fixed amplitude and an exactly fixed rate of change in the way a classical field might. Each mode of a free quantum field behaves mathematically like a harmonic oscillator, and even its ground state carries irreducible fluctuations. For a single ideal oscillator, the lowest energy is 1/2 of Planck's reduced constant, multiplied by its angular frequency, and a field contains an enormous collection of such modes. A naive sum of their ground state energies diverges, revealing not that nature contains a simple, infinite reservoir waiting to be extracted, but that the relation between vacuum energy and gravity requires careful renormalization and ultimately a deeper understanding than present theories fully provide. In non-gravitational quantum field theory, only differences in energy often affect measurable predictions, allowing an arbitrary reference level to be subtracted. Gravity is less forgiving because, in general relativity, absolute energy density contributes to space-time curvature. This tension lies behind the cosmological constant problem. Estimates based on known quantum fields appear extraordinarily difficult to reconcile naturally with the small effective vacuum energy inferred from the accelerating expansion of the universe. The observational phenomenon commonly attributed to dark energy behaves within the simplest model, like a cosmological constant with nearly uniform density and negative pressure. But whether this quantity is literally the vacuum energy of quantum fields, a dynamical field, a modification of gravity, or something not yet understood remains unsettled. The uncertainty does not weaken the essential point. A vacuum can influence cosmic evolution. It can possess an equation of state, contribute to expansion, and determine the large-scale fate of spacetime without containing ordinary atoms or light. The quantum vacuum also reveals itself through differences imposed by boundaries and environments. In the Casimir effect, conducting surfaces alter which electromagnetic field modes are permitted between and around them, producing a measurable force whose successful description depends on quantum field theory. The effect is sometimes presented as direct proof that empty space is filled with an unlimited sea of energy, but the accurate interpretation is subtler. Observable forces arise from how the quantum state and allowed modes differ between configurations. Related vacuum effects appear in atomic energy shifts, spontaneous emission, and the polarization of fields around charges, where the properties of what seems empty participate in measurable phenomena. Even the word vacuum is therefore contextual. The vacuum of one observer may not always match the vacuum identified by another observer following a different motion or inhabiting a different spacetime. In the Unruh effect, a uniformly accelerating observer is predicted to describe the Minkowski vacuum as a thermal state, while an inertial observer describes it as containing no particles. Near black holes, the definition of particles depends on the global structure of spacetime and the choice of quantum state, contributing to the theoretical prediction of Hawking radiation. These examples do not mean that reality becomes arbitrary or that observers may invent particles at will. They mean that the division of a quantum field into particles and vacuum depends on the modes used to describe it, especially in curved or non-inertial settings. The field is more fundamental than the particle count, and the vacuum is a structured state, rather than an eternally universal emptiness, perceived identically by everyone. This becomes crucial when we return to the possibility of something lying between two universes, because the phrase empty vacuum does not identify a unique substance. A vacuum state is defined by the fields, symmetries, geometry, and boundary conditions of the theory. Different configurations may have different energies and different physical properties, even when neither contains particles in the ordinary sense. A scalar field, for example, may possess a potential energy landscape with more than one local minimum. A field resting near one minimum can define one vacuum, while a second minimum defines another. The higher minimum may be metastable, meaning that it behaves as a stable state for an extremely long time, even though a lower energy state exists. This is called a false vacuum, while the lower state is often called a true vacuum, although in a complicated theory, even that lower state may not be the absolute final minimum. Quantum tunneling can, under suitable conditions, allow a small region of the lower energy phase to nucleate within the higher energy phase. The boundary of that region is not the edge of existence. It is a zone in which the field changes from one vacuum configuration to another, carrying energy associated with the gradient of the field and the tension of the wall. If the new phase is energetically favored and the dynamics permit it, the bubble may expand, converting the surrounding vacuum. In a cosmological setting, gravity modifies this process, and the resulting spacetime can be far more intricate than a bubble expanding through a motionless laboratory. The false vacuum may drive accelerated expansion, The interior may develop its own cosmological evolution, and horizons may prevent distant regions from sharing information. Under certain speculative models, what we call separate universes could be domains born from different vacuum transitions. In that case, the region between them might consist of the original false vacuum, perhaps still inflating, together with the moving walls that distinguish one phase from another. Yet this answer carries an important logical consequence. If there is a vacuum between the two universes, then that vacuum has fields, energy, geometry, and duration, which means it belongs to a larger physical framework containing both. The two universes would not be entirely separate realities in the strongest possible sense. They would be regions within a more encompassing spacetime or theory. True nothingness would be something radically different. It would contain no quantum fields waiting in their ground states, no metric defining distance, no clock marking duration, no laws specifying possible transitions, and no background in which a bubble could appear. Physics is extraordinarily successful at describing vacuum states, low-density regions, symmetric configurations, and even proposals for quantum creation. But these are never automatically descriptions of philosophical nothing, because every calculation begins with some structure: a state space, an action, an equation, a set of possible histories, or a rule assigning amplitudes. To say that a universe emerged from a quantum vacuum is therefore not to say that it emerged from the complete absence of everything. It means that a state lacking conventional matter may have evolved or tunneled into a different state under a specified theoretical framework. This quiet distinction prevents a great deal of confusion. The darkness between galaxies is not nothing because it contains fields and expanding geometry. A region without particles is not nothing because it can possess a quantum state. A false vacuum is not nothing because it can store energy and undergo decay. Even an ideal classical vacuum is not nothing if space-time remains there to define motion and causality. So if two universes are separated by a cosmic void, the void may be one of the most physically consequential parts of the entire picture, governing whether the universes can form, whether their boundaries expand, whether they can collide, and whether any signal could ever cross from one to the other. The absence of stars does not mean the absence of structure, and the absence of matter does not mean the absence of reality. In the deepest silence the cosmos can provide, the fields remain, the geometry remains, and the possibility of change remains, waiting without sound in what our eyes would call empty space. If two universes could be seen from some impossible vantage point, the mind would probably picture them as luminous spheres, drifting through a black and silent expanse, separated by an ocean of emptiness. Yet the most serious version of the bubble universe idea is stranger and more precise than that image, because the space between such universes would not be ordinary darkness at all, but a high-energy vacuum still undergoing inflation, a restless background whose expansion may continually create new cosmic regions while carrying older ones beyond one another's reach. To understand how this possibility emerged, we have to return to the early 20th century, when the discovery that distant galaxies are generally receding transformed the universe from a static arrangement into an evolving geometry. General relativity allowed space itself to expand, and the Friedmann equations connected the rate of that expansion to the density and pressure of cosmic contents. Yet the classical hot Big Bang picture left several puzzles. Regions of the cosmic microwave background now separated by enormous distances possess nearly the same temperature, even though, in a simple non-inflationary history, they would not have had enough time to exchange light and reach thermal equilibrium. The observable universe also appears remarkably close to spatial flatness, a condition that would have required extremely precise initial values if the early expansion had always proceeded at the slower rates associated with radiation and matter. In the late 1970s and early 1980s, physicists including Alexei Starobinsky, Alan Guth, Andre Linde, Andreas Albrecht, and Paul Steinhardt developed models in which the very young universe passed through a brief phase of accelerated expansion. During inflation, the energy density could be dominated by a field or effective vacuum state with pressure sufficiently negative that the scale factor grew almost exponentially. A microscopic region could then be stretched to dimensions far larger than the portion we can observe, smoothing curvature, diluting unwanted relics, and allowing formerly connected regions to acquire nearly uniform conditions before being carried far apart. Quantum fluctuations in the inflationary fields would also be stretched to astronomical scales, providing seeds from which galaxies and clusters could later grow, a broad prediction supported by the nearly scale-invariant and predominantly adiabatic pattern measured in primordial fluctuations, although the precise identity of the inflationary mechanism remains unknown. The next step toward bubble universes came from noticing that inflation does not necessarily end everywhere at once. In many models, the field responsible for inflation evolves probabilistically as well as classically. Its average motion may carry it toward a lower energy state where inflation ends, but quantum fluctuations can push it upward in some regions or delay its descent. If the physical volume of the still inflating domain grows faster than that domain decays, then inflation can end locally while continuing indefinitely on the largest scales. This is the essence of eternal inflation, not a claim that our own observable universe has existed eternally into the past, but the possibility that once inflation begins under suitable conditions, the total inflating volume never disappears, because new expanding regions are produced faster than old ones convert into non-inflating phases. In one family of models, especially those involving a metastable false vacuum, the transition occurs through quantum tunneling. A small bubble of a lower energy vacuum nucleates within the higher energy background, much as a new phase can appear inside a supercooled liquid, though the analogy is incomplete because spacetime geometry itself participates in the process. The bubble begins at a microscopic scale determined by the field potential and gravitational dynamics. Then its wall accelerates outward, often approaching the speed of light relative to nearby observers. Inside, the geometry need not resemble the interior of a tiny sphere sitting in a laboratory. The bubble's spatial slices can form an open, expanding universe, and a later period of slow-roll inflation within the bubble may make its interior vast, smooth, and nearly flat. Reheating can convert field energy into particles and radiation, beginning a hot cosmological history that may resemble our own. For observers who eventually arise there, the bubble would not appear as a small object with a visible center and enclosing shell. Their observable universe could look homogeneous in every direction, while the wall remains far beyond their horizon or forever inaccessible. If another bubble nucleates elsewhere, then the answer to what lies between the two is, within this model, remarkably direct. The region between them is the parent false vacuum, still carrying the energy that drives accelerated expansion. Yet even this sentence must be handled carefully, because the false vacuum is not a static sea through which the bubbles simply drift. Its metric is changing. Physical distances within it can grow exponentially, and this growth competes with the outward motion of the bubble walls. Locally, no material boundary outruns light, but globally, the background can create new space so rapidly that widely separated bubbles may never meet. Two walls can both expand almost at light speed into their surroundings, while the inflating interval between them increases faster than either can cross it. Not because anything travels through space faster than light, but because general relativity places no comparable limit on the rate at which sufficiently distant co-moving separations may grow. This creates a universe of extraordinary structure. Pockets where inflation has ended, surrounded by regions where it continues, with new pockets constantly forming while the total inflating volume expands without limit. The word sea is useful because it evokes continuity, but the false vacuum is not a substance with a preferred rest frame in the ordinary mechanical sense. It is a state of one or more fields, together with a space-time geometry determined by their energy and pressure. Its expansion rate is related to the vacuum energy through the Friedmann equation. So a higher effective vacuum density generally corresponds to a larger Hubble parameter for the inflating region. The decay rate is usually described probabilistically per unit 4 volume, meaning that the longer inflation continues and the more space-time volume it produces, the more opportunities exist for bubbles to nucleate. Whether eternal inflation actually occurs depends on the detailed balance between these rates, the form of the potential, gravitational back reaction, and the treatment of quantum fluctuations. It is therefore not a universal consequence of every inflationary theory. Some models may avoid it, while others seem to produce it naturally, and present observations do not establish which family, if any, describes nature. If two bubbles form close enough, their expanding walls may eventually collide. The collision would not resemble two soap bubbles touching gently in still air. Each wall can contain concentrated gradient and potential energy, while the geometry around it may be highly relativistic. Depending on the vacua involved, the encounter could merge similar phases, create a new domain wall, redirect energy into radiation, or produce a disturbed region whose subsequent expansion differs from the undisturbed interior. In principle, if our observable cosmos lay within the future light cone of such a collision, the event might leave a broad, approximately disc-shaped signature in the cosmic microwave background, along with correlated polarization or large-scale structure. Searches have placed constraints on simple versions of these signals, but no bubble collision has been confirmed, and apparent anomalies in the sky have not reached the level required to establish another universe. The absence of a detected signature does not eliminate the entire framework, because collisions may be rare, their signals may be too weak, inflation inside our bubble may have diluted them, or the relevant models may predict patterns beyond current sensitivity. Still, the need for observational consequences remains essential. Without some possible trace, the image of an endless false vacuum sea would remain a mathematically motivated extension rather than an empirically established landscape. The model also confronts a deeper difficulty known as the measure problem. Eternal inflation may generate infinitely many bubbles of many types, and once infinities appear, ordinary counting becomes ambiguous. Different ways of slicing spacetime or regulating the infinite ensemble can assign different relative probabilities to what observers should expect to see. A theory that produces every allowed event, infinitely many times, cannot make clear predictions until it supplies a defensible rule for comparing those infinities. This unresolved issue does not prove eternal inflation wrong, but it shows that producing a multiverse is easier than turning that multiverse into a complete predictive framework. There is also no guarantee that every bubble contains familiar matter, stable atoms, or even the same low-energy laws. If the underlying theory admits multiple vacuum states, each bubble could settle into a different configuration of fields, symmetries, particle masses, or effective constants. The tranquil word universe may then describe regions radically unlike one another, some collapsing quickly, some expanding too rapidly for structure to form, and some perhaps capable of stars, chemistry, and observers. Yet all of them would still be related through the parent theory in the inflating background, so they would not be wholly independent realities without common structure. The false vacuum between them would be part of the larger spacetime that gives the phrase "between" its meaning. This is the central distinction. If there is a measurable region separating two universes, then those universes are domains within something more extensive than either one alone. Their apparent isolation comes from horizons, expansion, and incompatible histories, not from the complete absence of a shared physical framework. And so the picture gradually settles into focus. Between two bubble universes, there may be no quiet corridor waiting to be crossed, no calm black emptiness where a traveler could pause midway and look toward both shores. There may instead be an inflating vacuum, whose geometry stretches relentlessly, a parent state capable of spawning new cosmic domains while pushing existing ones beyond causal contact. It would be empty of ordinary galaxies, and perhaps nearly empty of particles, yet filled with field energy, expansion, and unrealized possibilities. In that immense and almost featureless background, universes would not merely sit apart like islands in a dark ocean. The ocean itself would grow, and with each silent increase in its volume, the distance between worlds could become not only vast, but permanently uncrossable. If two universes were ever separated by something narrow enough to be called a wall, it would not resemble stone, metal, glass, or any other substance that a traveler could approach and touch. Because in modern field theory, a cosmic wall is not primarily an object placed inside space. It is a region where the physical state of space changes, a thin transition across which one set of field values gives way to another. Imagine a landscape not made of mountains and valleys in ordinary distance, but of possible configurations of a field, with each valley representing a vacuum state and each slope representing the energy required to move away from it. If one region of the cosmos settles into one valley, while a neighboring region settles into another, the field cannot usually jump discontinuously from one value to the other at a perfectly sharp surface, because abrupt changes would produce infinite gradient energy. Instead, the field passes smoothly, though perhaps rapidly, through intermediate values, creating a layer whose thickness is determined by the shape of the potential, the mass scale of the field, and the strength of the interactions involved. This layer is what physicists call a domain wall, and although it may be extremely thin compared with the size of the universes on either side, it can still contain immense energy per unit area. The word thin is therefore relational rather than absolute. A wall could be microscopic on cosmological scales, while remaining vastly larger than an atomic nucleus, or it could arise near energies so high that its internal structure would be inaccessible to any present experiment. In the thin wall approximation, the detailed transition is compressed mathematically into an idealized surface with a tension, much as a soap film can be treated as a surface even though its molecules occupy a finite thickness. This approximation, developed in the study of vacuum decay, allows the complicated field profile to be replaced by a simpler boundary separating regions with different vacuum energies. Yet, unlike a soap film, the wall does not merely respond to spacetime. Through its energy and tension, it also gravitates, bending the geometry around itself and altering the motion of the regions it divides. The earliest systematic quantum description of false vacuum decay was developed by Sidney Coleman, and the inclusion of gravity by Coleman and Frank DeLucia revealed that a nucleating bubble must be understood as both a field configuration and a spacetime geometry. The probability of its appearance is related GCC-Gickley to an instanton, a solution formulated in Euclideanized spacetime that describes the tunneling path between vacuum states. After analytic continuation back to Lorentzian time, the bubble evolves dynamically, and its wall accelerates according to the difference in vacuum energy across it, its own tension, and the surrounding curvature. This means the wall is never just a passive border. It is a physical participant in the history of both domains. If the interior vacuum has lower energy than the exterior, the conversion can be energetically favored, yet the surface tension resists the formation of small bubbles, because a small bubble has a large wall area relative to its volume. Only when a fluctuation creates a bubble beyond a critical size can the gain in volume energy overcome the energetic cost of the wall, allowing expansion to proceed. Gravity complicates even this simple balance. A sufficiently high vacuum energy can drive accelerated expansion. A sufficiently strong wall tension can reshape causal structure. And in some solutions, the region that appears to expand from one viewpoint may be hidden behind a horizon from another. The language of a wall moving through space can therefore be useful locally, but incomplete globally, because the wall and the space around it form one coupled relativistic system. When two bubble universes approach one another within an inflating background, their first contact is not the meeting of two rigid shells. Each wall is a moving concentration of field energy, and the fields on either side may correspond to identical vacua, different vacua, or phases connected by a more complicated path through configuration space. If the interiors share the same vacuum, the colliding walls may annihilate or pass their energy into radiation and field excitations, leaving behind a merged domain whose geometry gradually relaxes. If the interiors occupy different vacua, a new domain wall can remain between them, separating the two phases after the original bubble walls have collided. The motion of this surviving wall depends strongly on the difference in vacuum energy. In many idealized cases, it accelerates away from the region with higher vacuum energy and toward the lower energy side, although gravity and wall tension can modify the intuitive picture. The matching of two spacetime regions across such a thin surface is often analyzed using the Israel junction conditions, which connect the discontinuity in extrinsic curvature to the stress energy localized on the wall. These conditions are not merely technical decoration. They express a deep requirement that the geometry on both sides and the energy carried by the boundary fit together consistently. A wall with tension changes how neighboring geodesics diverge, how clocks accumulate proper time, and whether light emitted near the boundary can ever reach distant observers. In some solutions, the wall's gravity is effectively repulsive, not because it violates ordinary gravitational principles, but because tension contributes to stress energy differently from pressureless matter. General relativity responds not only to mass density, but also to pressure and stress, and the negative pressure associated with a domain wall can produce geometry unlike the familiar attraction of a star or planet. To an observer far inside one bubble, the collision may not appear as a bright object racing across an otherwise calm sky. Its observable imprint would depend on when the collision occurred. how much inflation followed it, and whether signals from the disturbed region could enter the observer's past light cone. A long period of inflation inside the bubble could stretch and dilute the collision's effects until only a broad modulation remained, perhaps appearing as a disk-like pattern in the cosmic microwave background, a directional variation in primordial perturbations, or a correlated polarization signal. Searches for such signatures have not produced confirmed evidence of a neighboring bubble, and many apparent anomalies can arise from statistical fluctuations, foreground contamination, or conventional cosmological processes. The scientific value of these searches lies not in proving that every unusual patch of sky is a scar from another universe, but in translating speculative models into patterns that data can constrain. Even a null result can eliminate portions of parameter space by limiting the possible collision rate, energy scale, wall tension, or amount of inflation that could have followed. If the wall itself were somehow nearby, the notion of standing upon it would still be misleading. Stable matter depends on the vacuum structure that determines particle masses, interaction strengths, and the form of bound states. Inside the transition region, those quantities may vary. The Higgs field or other fields could take values unlike those that permit ordinary atoms, and the wall's concentrated energy could produce extreme tidal forces, particle creation, or violent interactions with any material attempting to cross. There may be no stationary frame in which a traveler could hover midway, because the wall is generally accelerating and may possess no globally defined rest state across the entire geometry. Even the idea of two clocks, one on each side, ticking against a common universal time can fail. Relativity provides proper time along individual world lines, but a global notion of simultaneity depends on the space-time structure and the slicing chosen to describe it. Two bubble interiors may possess different expansion histories, different reheating times, and different natural cosmological clocks. Asking which universe is older may therefore require specifying how events across the wall are compared. A coordinate system can assign labels, but coordinate labels are not themselves observable facts. What remains invariant are causal relations, proper intervals, curvature, and the physical behavior of fields. The wall also raises a subtle question about identity. If the constants of nature differ across it, are the two sides truly different universes, or merely different phases of one deeper theory? From the viewpoint of the underlying equations, they may be neighboring solutions connected by a field trajectory. From the viewpoint of observers whose matter can exist only on one side, the boundary may be as final as the edge of their physical world. This is why a domain wall can function as a border between realities without being the end of spacetime. It separates regimes in which the same fundamental framework manifests differently, much as water and ice are phases of one molecular substance. Though the cosmological transition may alter far more than density or structure, it may change symmetry, particle spectra, vacuum energy, and the entire future evolution of the surrounding geometry. In some theories, walls are stable because the vacua belong to disconnected sectors of the field configuration space. In others, they are metastable and can decay by nucleating holes bounded by strings or through transitions to a lower energy phase. Their persistence depends on topology, dynamics, and the available decay channels, so no universal wall exists with one fixed thickness, lifetime, or behavior. Cosmology has also placed strong limits on ordinary domain wall networks within our observable universe, because a population of stable walls could contribute energy in a way that rapidly dominates cosmic evolution and produces anisotropies inconsistent with observation. This historical difficulty helped motivate models in which any primordial walls are inflated away, rendered unstable, or associated with scales and abundances too small to conflict with data. Yet the walls separating hypothetical bubble universes belong to a broader and more model-dependent setting, often far outside our horizon, where their observational consequences may be indirect or permanently inaccessible. The answer to what sits directly between two universes can therefore become surprisingly narrow. It may not be a vast region at all. It may be a field transition compressed into a layer, a place where one vacuum ends not at an edge, but through a continuous rearrangement of physical possibility. On one side, particles may have one set of masses and forces. On the other, they may have another. Within the wall, the laws do not vanish, but the state on which those laws act is changing. The boundary may expand, curve, collide, radiate, or retreat, carrying enough tension to influence the shape of space-time itself. And in that nearly invisible layer, thinner than the cosmic domains it divides, yet powerful enough to govern their encounter, the distance between two realities may be reduced to the quiet passage of a field from one valley of existence into another. Imagine that everything we call the universe, the galaxies, the cosmic microwave background, every atom in every body, and even the three directions through which we move, belongs to an immense surface suspended within a deeper geometry that our senses cannot enter. And then imagine another such surface lying somewhere across that unseen depth. In this family of theories, the answer to what sits between two universes becomes unusually literal, because between them there may be a higher dimensional region called the bulk. The idea begins with a change in what physicists mean by dimension. A dimension is not simply a visible direction drawn on a diagram, but an independent coordinate needed to specify an event. Our familiar spacetime uses 3 spatial coordinates and 1 time coordinate, yet mathematics permits manifolds with additional directions, and physics has explored them for more than a century. In the 1920s, Theodore Kaluza and Oscar Klein showed that a 5-dimensional gravitational theory could appear after one dimension was compactified into a tiny circle, as 4-dimensional gravity accompanied by equations resembling electromagnetism. The proposal did not become a complete description of nature, but it established a powerful principle. Motion and geometry in hidden dimensions can appear to lower dimensional observers as particles, fields, and forces. Later string theory required additional spatial dimensions for mathematical consistency, while M-theory broadened the fundamental objects from one-dimensional strings to extended entities of several dimensions. A point-like object may be called a zero brane, a string a one brane, a membrane a two brane, and an object with 3 spatial dimensions a 3 brane, or 3 brane. If our observable cosmos were associated with a 3 brane, ordinary space would not be the container holding that brane. Ordinary space would be part of the brane itself, while the bulk would supply at least one additional direction transverse to it. This creates a subtle form of confinement. In many brane world models, the particles and gauge interactions of the standard model are localized on the brane, so electrons, quarks, photons, and the forces binding atoms cannot simply drift away into the extra dimension. Their allowed quantum states remain attached to the brane, rather as waves can be guided along a surface, although the underlying mechanism is described through fields and symmetries rather than mechanical glue. Gravity is often permitted to propagate through the bulk because it is identified with the geometry of the full higher dimensional spacetime. From inside our universe, gravity would then seem extraordinarily weak. Not necessarily because its fundamental strength is tiny, but because part of its influence spreads through dimensions unavailable to the other interactions. This possibility helped motivate large extra-dimension models, and, in a different way, the warped geometries introduced by Lisa Randall and Raman Sundram in 1999. Their 2-brane construction placed 2 3 branes at different locations along a compact 5th dimension within a slice of 5-dimensional anti-de Sitter space. The metric included a warp factor that changed exponentially along the extra coordinate, so physical energy scales measured on one brane could be dramatically smaller than scales on the other, even when the geometric separation was not enormous. The hierarchy between the electroweak and Planck scales could then arise from geometry, rather than from an unexplained tiny number inserted by hand. In a related one-brane model, the extra dimension could extend without ordinary compactification, while curved bulk geometry still localized a low-energy gravitational mode near the brane, allowing 4-dimensional gravity to emerge over accessible distances. These constructions do not establish that our universe is a brane, but they demonstrate mathematically that an unseen dimension need not behave like a simple empty hallway, and that its curvature can determine how strongly one universe feels another. The bulk in such models may possess its own cosmological constant, curvature, scalar fields, gravitational waves, and towers of Kaluza-Klein modes. To a 4-dimensional observer, momentum in the hidden direction can appear as a sequence of massive particles, with greater transverse momentum corresponding to larger effective mass. A disturbance traveling through the bulk might therefore be described on the brane not as an object leaving our sky, but as an altered gravitational signal or a massive excitation. The geometry can also be warped so strongly that equal coordinate intervals at different bulk locations correspond to very different physical scales, which means the phrase distance between branes cannot be understood by drawing two parallel sheets and measuring the blank space with an ordinary ruler. The proper separation must be calculated from the higher dimensional metric, and that separation can itself become dynamical. In a two-brane system, fluctuations in the size of the extra dimension appear in the lower dimensional effective theory as a scalar degree of freedom commonly called the radion. The radion is one of the most revealing ideas in the entire picture because it translates the distance between universes into something inhabitants of a brane might experience as a field. If the radion changes from place to place or evolves with time, the inner brane separation changes, potentially modifying gravitational strength, particle scales, or cosmic expansion. An unstabilized radion would generally create unacceptable variations, so viable models require a mechanism that fixes the branes at a suitable average separation. Goldberger and Wise proposed that a scalar field living in the bulk could develop a profile between the branes and generate an effective potential for the radion, allowing the extra dimension to settle near a stable size. The space between the universes would then not merely separate them, fields within it would help determine why that separation persists. The bulk could act as a quiet geometric reservoir, whose configuration sets the energy scales observed on each brane, while remaining almost invisible to matter confined upon them. Cosmology makes this hidden interval more dynamic. A brane moving through a static-looking bulk can be described equivalently, under appropriate coordinates, as an expanding universe with matter on the brane. The effective Friedmann equation governing that expansion may contain corrections absent from standard four-dimensional cosmology, including terms quadratic in the brane's energy density and contributions sometimes described as dark radiation, arising from the geometry or black hole mass parameter of the bulk. At sufficiently low energies, these corrections can become small and ordinary cosmology can re-emerge, but in the early universe they could alter expansion, nucleosynthesis, perturbation growth, or gravitational wave propagation. Observations therefore constrain how large, curved, or strongly coupled the extra dimensions may be, while laboratory tests of gravity and collider searches restrict particular realizations. No confirmed deviation has yet required a brane world explanation, and the broad variety of models prevents a single null result from excluding the entire idea. The most dramatic possibility arises when the separation between branes is allowed to evolve toward zero. In ekpyrotic and cyclic scenarios, versions of the hot Big Bang have been modeled not as the absolute creation of space and time, but as the outcome of an encounter between branes. As the branes approach through the bulk, their relative position can appear in a four-dimensional description as a scalar field rolling through an effective potential. A slowly contracting ekpyrotic phase may suppress curvature and anisotropy under suitable conditions, after which the collision or bounce is proposed to convert part of the brane's kinetic energy into matter and radiation. The apparent beginning of the hot expanding universe would then correspond to a violent event in the hidden dimension. Some cyclic versions imagine repeated approaches and separations, giving cosmic history a sequence of phases, rather than a single beginning. These proposals remain actively debated because the collision can involve singular behavior, the conversion of perturbations must be controlled, and a complete treatment may require quantum gravity. Their observational predictions also depend on the detailed model, and current data do not establish that a brane collision occurred, yet they sharpen the tidal question in a remarkable way. If two universes are branes, the thing between them may be neither philosophical nothingness nor the false vacuum of bubble cosmology, but a bulk with measurable curvature, field content, and dynamical depth. It may carry gravity from one brane toward the other while preventing light and ordinary matter from following. It may contain a stabilizing scalar field whose profile fixes the distance between cosmic worlds. It may be warped so that a modest step through the fifth dimension corresponds to an enormous change in physical scale. It may even allow the branes to move, approach, collide, and retreat, turning their separation into part of cosmological history. From our side, this hidden distance would not appear as an open direction in the night sky, because every telescope, detector, and human eye is built from fields confined to the same brane. We might look directly toward the extra dimension without seeing a direction at all, just as a figure drawn on a page cannot turn its gaze above the paper if every part of the figure is restricted to the page. Only gravity, or another field permitted to inhabit the bulk, might carry a faint report of what lies beyond. And so, within this carefully defined but unconfirmed framework, two universes could be closer than any neighboring galaxies, while remaining inaccessible to one another, separated not by trillions of light years along our space, but by a distance measured in a direction that our matter does not know how to travel. Between them would lie the bulk, not an empty darkness, but the deeper geometry from which their apparent isolation, their gravitational behavior, and perhaps even the scale of their physical laws quietly emerge. When people hear that quantum mechanics may allow many worlds, the mind almost immediately arranges those worlds like parallel corridors, each one running beside the others through a vast and invisible darkness. Yet this familiar image is not what the mathematics actually describes, because quantum branches are not separate spheres floating at different locations, and there is no empty region through which one could travel from one branch to another. The distinction begins with superposition, one of the most tested and least intuitive features of quantum theory. A classical object is usually described as having a definite state, even when we do not know what that state is. But a quantum system can be represented by a state that combines several possible outcomes with complex amplitudes. These amplitudes are not ordinary probabilities because they can interfere, strengthening some outcomes and canceling others, as waves do when their crests and troughs overlap. In the double-slit experiment, a particle sent one at a time can gradually form an interference pattern, revealing that its quantum state evolved through alternatives whose amplitudes remained coherent enough to combine. The mystery deepens when the system being measured is included in the same description. If a microscopic object begins in a superposition and interacts with a measuring device, the Schrödinger equation does not ordinarily select one result by itself. It produces an entangled state in which one state of the device is correlated with one possible outcome, and another state of the device is correlated with another. If an observer then becomes physically correlated with the apparatus, the mathematical description expands again, linking each recorded result with a corresponding state of the observer. Hugh Everett's relative state formulation, introduced in 1957, took this unitary evolution seriously and proposed that the different correlated components need not be reduced by a special physical collapse. What later came to be called the many worlds interpretation developed from this idea, though the word world can make the structure sound more spatial and more sharply divided than the formalism itself requires. The branches are components of a quantum state, not planets placed on opposite sides of an unobserved void. To understand their separation, one must leave ordinary three-dimensional space and enter Hilbert space, the abstract mathematical space in which quantum states are represented. A point in ordinary space tells us where an object is located, while a vector in Hilbert space encodes amplitudes for all the outcomes associated with a chosen set of observables. The number of dimensions in this state space can be enormous, and for a field with infinitely many degrees of freedom, it may be formally infinite dimensional. But those dimensions are not hidden compass directions that a spacecraft could enter. They correspond to independent ways the state can vary. Two quantum states can have an inner product that measures their overlap, and when that overlap approaches zero, they are described as orthogonal. Orthogonality is a kind of distinguishability in state space, not a physical gap measured in miles. This is the first direct answer to what lies between two quantum branches. No intervening substance is required, because their separation is expressed through vanishing overlap and lost interference, rather than through distance. The process that makes this separation appear stable is decoherence. No macroscopic object is truly isolated. A dust grain in interstellar space is struck by photons, gravitationally influenced by surrounding matter, and coupled to fields that carry away information about its position and motion. A laboratory detector interacts with air molecules, thermal radiation, its support structure, and countless internal degrees of freedom. Each interaction entangles the system with its environment. If one possible state of the system leaves one pattern in the environment, while another possible state leaves a distinguishable pattern, then the environmental records rapidly become correlated with the alternatives. An observer who has access only to the system, and not to every microscopic detail of the environment, describes the system with a reduced density matrix, obtained mathematically by tracing over the inaccessible environmental degrees of freedom. In a suitable basis, the off-diagonal terms that encode observable interference become extremely small. This suppression does not necessarily destroy the total superposition in the universal state, but it prevents the separate components from interfering in any practical local experiment. Decoherence can occur with astonishing speed for macroscopic systems, because each escaping photon or collision carries another fragment of which state information into the surroundings. The environment therefore acts not as a conscious observer, but as a vast record-making network. Certain robust states, often called pointer states, survive this continual monitoring more stably than delicate superpositions, helping explain why the world appears to contain objects with approximately definite positions, trajectories, and records. Classical reality emerges not because quantum mechanics stops operating, but because the correlations needed to observe interference become dispersed into an uncontrollably large environment. This also explains why the popular phrase, "every decision creates a new universe," is misleading. Branching is not triggered by human choice, intention, or awareness. It arises whenever interactions produce effectively irreversible records among quantum degrees of freedom, which occurs throughout nature continuously, long before life appears. Nor is there a unique instant at which one perfectly defined world splits into two. Decoherence is gradual, approximate, and dependent on how the system is divided from its environment. Different coarse-grained descriptions may identify branches at different levels of detail, and the number of branches is not generally a simple countable total that increases each time someone chooses tea instead of coffee. The branching picture is a useful emergent description of a continuously evolving quantum state, not a literal tree carved into a separate spatial dimension. If two branches later became capable of interfering again, they would not have traveled back toward one another through an empty corridor. Their environmental correlations would have to be reversed or controlled with extraordinary precision so that the relative phases between the components became observable once more. Small systems can be recohered in carefully designed experiments because only a limited number of degrees of freedom have carried away information. For a macroscopic event, however, the relevant correlations spread into air, light, heat, instruments, neural states, and distant surroundings. Reversing them would require controlling an immense web of physical records, with accuracy far beyond present capability. The barrier between branches is therefore not a wall, but practical irreversibility produced by entanglement and complexity. In principle, under strictly unitary quantum mechanics, the complete state retains all amplitudes and their phase relationships. But from inside a branch, the inaccessible alternatives behave as though they have become separate histories. The word history is especially important in quantum cosmology, where physicists sometimes study sets of coarse-grained histories rather than instantaneous worlds. A history may specify ranges of field values, geometries, or large-scale events across time, and a collection of histories can be assigned probabilities only when interference between them is sufficiently suppressed. In the decoherent histories approach, the consistency of such alternatives is examined through a decoherence functional, which measures whether cross-terms between histories are negligible. When they are, ordinary probabilistic reasoning becomes possible. These histories do not need to inhabit neighboring universes. They are alternative, internally correlated patterns within the quantum description. The same caution applies when quantum mechanics is extended to the entire cosmos. There may be no external observer standing outside the universe to perform a measurement. So, quantum cosmology seeks formulations in which observers, apparatus, and environments are all subsystems of one larger state. Different interpretations then disagree about what the mathematical structure means. Ever-ready approaches treat the branches as equally real components of the universal wave function. Collapse theories add new dynamics that genuinely remove or localize alternatives. Copenhagen-like views may resist assigning a single, observer-independent story to the wave function of the whole universe. Relational and information-centered interpretations offer still other accounts. These perspectives often reproduce the same laboratory predictions over broad domains, so decoherence by itself does not prove that many worlds exist as independent realities. It explains why interference becomes unobservable and why classical records emerge, but the ontological conclusion remains interpretive. Even so, if one chooses to speak of quantum universes, the geometry of their separation is clear enough to prevent a common mistake. They do not lie beyond one another's horizons in ordinary space. A galaxy in another branch is not farther away than the most distant galaxy we can see. It may be represented at the same spatial coordinates within a different component of the quantum state, correlated with a different chain of records. There is no midpoint where half of one history blends spatially into half of another, because the distinction belongs to state space and entanglement structure. What sits between the branches is not dark matter, vacuum energy, a brane, or a hidden ocean. At most, one can speak metaphorically of decoherence, the fading of accessible phase relations, the dispersal of information into the environment, and the near orthogonality of macroscopic records. The total quantum state may still contain both possibilities, yet each observer finds a consistent past written into the world around them, from the detector reading nearby to the photons already traveling outward into space. And so two quantum realities can be profoundly separated without being spatially apart, divided not by emptiness, but by the quiet multiplication of correlations, until the path from one history to another is lost not across distance, but within the almost immeasurable complexity of the state itself. Suppose two universes do not differ because they occupy distant regions of space, but because the fields underlying matter and force have settled into different configurations, and then the question of what lies between them changes once again, becoming less like a journey across darkness and more like a path across the hidden geography of physical possibility. A field assigns a value to every point of spacetime, yet we can also imagine the collection of all values the field could take. For a single homogeneous scalar field, that collection may look like a line, with each point representing one possible value. For two scalar fields, it becomes a surface, and for many fields, it becomes a high-dimensional manifold called field space. Its coordinates do not tell us where an object is located. They specify which physical configuration is being considered. If the fields determine particle masses, interaction strengths, symmetry breaking, or the shape of compact extra dimensions, then 2 points in field space may correspond to worlds whose low-energy physics is profoundly different, even though no ordinary spatial displacement separates them. The simplest picture draws a potential V above this space, turning it into a landscape of valleys, ridges, and passes. A stable or metastable vacuum lies near a local minimum, where small disturbances tend to oscillate rather than roll away. A second minimum may define another vacuum with a different energy density or pattern of symmetry. If cosmological regions settle into those two minima, they may be spoken of as different universes, but the phrase distance between them refers first to the change in field values required to move from one vacuum configuration to the other. Even that distance is not found merely by subtracting coordinates. In a theory with several fields, the kinetic part of the action can contain a field space metric, usually written G sub ij, so an infinitesimal interval takes the form ds squared equals G sub ij d phi superscript I d phi superscript j. The proper length of a path depends on this metric, and the shortest route is a geodesic of the field manifold, rather than necessarily a straight line on a drawing. Curvature in field space can alter trajectories, perturbations, and stability, which is why modern multi-field cosmology often uses a covariant geometric formalism, instead of treating every field coordinate as globally flat. A change of variables may stretch or compress coordinate labels while leaving the proper distance unchanged, just as changing from miles to kilometers alters numbers without changing the road. Yet distance and difficulty are not the same thing. Two minima can be close in proper field distance, but separated by a high potential barrier, while two distant configurations may be connected by a gently sloping valley. Barrier height measures potential energy along a route. Field space length measures how far the configuration moves according to the kinetic geometry. And the tunneling rate depends on an action that combines both with the space-time profile of the transition. Nature does not generally select a path by asking only for the lowest ridge or the shortest line. In semicolon vacuum decay, the dominant transition is associated with a bounce or instanton, a special Euclidean solution that makes the action stationary and determines the leading exponential suppression of the decay probability. With several fields, the favored path can curve around a high barrier, pass near a saddle point, or exploit a direction hidden in a one-dimensional sketch. When gravity matters, space-time geometry joins the calculation, and some transitions can be enhanced, suppressed, or absent, depending on the vacuum energies and the gravitational solution. The instanton formalism, beginning with Coleman's treatment and extended to include gravity by Coleman and De Lucia, remains the standard seminar language for such processes, although its use becomes technically subtle in complicated theories. The configurations along the tunneling path should not be imagined as a sequence of long-lived universes sitting neatly between the endpoints. Most are unstable intermediate arrangements, and many are not classical worlds that could persist long enough to contain observers. They function more like points along the least action route through configuration space. After a bubble nucleates, the field varies across real space, from one vacuum to another, converting an abstract path in field space into a physical wall profile. As one crosses the wall spatially, the field traces a route across the landscape. The wall is a localized structure in spacetime, while the field space path is the sequence of values defining its internal transition. This distinction becomes more important in theories descended from additional dimensions. In string-inspired compactifications, the size and shape of hidden dimensions, the positions of branes, background fluxes, and other quantities can appear in 4 dimensions as scalar fields, known collectively as moduli. Different stabilized values of these moduli can produce different effective particle spectra, coupling constants, symmetry groups, and vacuum energies. Fluxes threading compact cycles may contribute to the moduli potential and help stabilize configurations that would otherwise drift, leading to a large collection of candidate vacua, often described as the string landscape. Reviews of flux compactification emphasize both the mechanisms that generate many candidate vacua and the unresolved question of which, if any, yield a fully controlled description of our universe. The landscape metaphor is powerful, but it must not be mistaken for a literal continent. Its mountains are energy barriers, its coordinates are fields and moduli, and its valleys are solutions, or approximate solutions, of an effective theory. A catalog of vacua is not automatically a population of existing universes. For a vacuum to become a cosmic region, some dynamical history must place the fields there, perhaps through inflationary evolution, tunneling, thermal transitions, or initial conditions. Some candidate vacua may be unstable, some may lack a controlled approximation, and some may belong to descriptions that cannot be smoothly connected within one effective field theory. 2 entries in a mathematical catalog may therefore have no physically realizable road between them. In other cases, transitions can form a network. Each vacuum is a node, each allowed decay a directed link, and the rates determine how probability might flow. Such a graph provides another meaning of neighborhood. 2 vacua can be adjacent because one can decay into the other, not because their universes sit side by side in ordinary space. A third vacuum may be close by field distance, yet dynamically unreachable if no finite action transition exists, while a distant vacuum may be reached through a chain of intermediate decays. The topology of the transition network can therefore matter as much as the geometry of field space. The idea of distance becomes more delicate near the boundaries of effective theory. The swampland distance conjecture proposes that when one moves an infinite proper distance in moduli space within a theory compatible with quantum gravity, an infinite tower of states becomes exponentially light, lowering the scale at which the original effective description remains valid. This is a conjecture supported by many string theory examples rather than an experimentally established law. But if it is broadly correct, the farthest regions of field space cannot be explored while keeping the same simple set of particles and equations. New degrees of freedom emerge, and the map redraws itself as the traveler approaches what looked like an infinitely distant frontier. Large field distance may therefore signal not merely a long journey through one theory, but the gradual failure of the theory used to define the journey. A further complication appears when these vacua are embedded in eternal inflation. If transitions continually generate regions of different types, and the process creates unbounded numbers or volumes of them, predicting which kind of universe is typical requires a probability measure. Different cutoffs or ways of regulating the infinite spacetime can assign different relative weights, and no universally accepted prescription has emerged. Studies of the measure problem show that distinct regularization choices can produce sharply different predictions, even for related inflationary models. A landscape may describe possible vacua, and a transition network may describe possible motion, yet neither alone tells us how frequently each universe should occur. The answer to what lies between two such universes is therefore not one object, but a hierarchy of structures. At the simplest level, there may be a continuous path of field configurations joining two minima. Along that path, there may be a potential barrier and perhaps a saddle point. The favored transition may be represented by an instanton whose action determines a decay rate. In real spacetime, that transition may appear as a bubble wall across which the fields trace the path. In a deeper theory, the endpoints may correspond to different compactifications, flux choices, or symmetry patterns, while the supposed route between them may require states omitted from the low-energy description. And if the vacua are entirely disconnected sectors, there may be no meaningful path at all. So the distance between universes may be measured without any ruler pointing through the night. It may be a geodesic length in a manifold of fields, an energetic barrier in a potential, a suppression encoded in an action, or a sequence of allowed transitions through a network of vacua. None of these is the same as spatial separation, and none guarantees that a traveler, or even a stable universe, can occupy the points in between. What appears from far away as a landscape of worlds is, at closer range, a map of changing laws, and the quiet territory between two universes may be nothing more and nothing less than the precise mathematical route by which one form of physical reality could become another. If something truly lies between two universes, then the most realistic hope of finding it may not be to look beyond the edge of our cosmos, because no telescope can turn toward a direction that space-time itself does not provide, but to search instead for a disturbance left behind when that hidden boundary once influenced the universe we can observe. Physics often discovers unseen structures in this indirect way. No one watches the interior of the sun with ordinary light, yet neutrinos and vibrations reveal what happens beneath its surface. No eye sees a black hole's event horizon as a material shell, yet the motions of stars, the glow of heated gas, and the ringing of gravitational waves betray the geometry nearby. A second universe, a domain wall, or a higher dimensional bulk might be approached by the same quiet logic. If it is ever touched, curved, pulled upon, or exchanged energy with our cosmic region, perhaps our sky still carries the imprint. The cleanest theoretical case comes from bubble universes born within false vacuum eternal inflation. If our observable universe developed inside one bubble, and another bubble collided with it during the early stages of expansion, the collision could have disturbed the inflaton field, altered the local reheating history, and changed the primordial curvature perturbations from which later cosmic structure grew. Because the collision has an approximate axial symmetry, its influence might appear on the celestial sphere as a broad circular or disk-like region, rather than as an ordinary point source. Within simplified models, the temperature across that region can vary smoothly toward a boundary, while the polarization pattern may possess a correlated symmetry that helps distinguish a primordial collision from foreground dust, instrumental noise, or a chance statistical fluctuation. Early searches in Wilkinson microwave anisotropy probe data found no evidence strong enough to justify adding bubble collisions to the standard cosmological model, and later work has continued to refine the predicted profiles, statistical methods, and use of temperature and polarization without producing a confirmed detection. This absence is meaningful, though it is not a universal disproof. The appearance of a collision depends on the field potential, the relative vacuum energies, the separation of the bubbles before contact, the trajectory and tension of the walls, and the amount of inflation that occurred afterward inside our own bubble. Too much later inflation would stretch the affected region beyond our observable horizon, or dilute its contrast until it became nearly indistinguishable from the ordinary primordial fluctuations. A collision occurring in the wrong causal location would never enter our past light cone at all. Even a visible signal might overlap with the random structure expected in the cosmic microwave background, and this leads to one of cosmology's deepest observational limits. We possess only one sky. At the largest angular scales, there are only a small number of independent modes available to measure, producing cosmic variance, an irreducible uncertainty that cannot be eliminated merely by building a quieter detector. Better instruments can reduce measurement noise and improve foreground removal. but they cannot provide another realization of the observable universe for comparison. Polarization can nevertheless add information, because the scattering of radiation responds to the local quadrupole pattern and may preserve a geometrically related trace of a collision. Future reconstructions of remote dipole and quadrupole fields, using the interaction of cosmic microwave background photons with matter at different distances, have been proposed as a way to sample large-scale conditions from locations other than Earth, and possibly weaken some limitations of the single local sky, though such methods remain prospective rather than confirmed routes to another universe. A surviving domain wall would produce a different family of clues. Its energy and tension would curve spacetime, alter the motion of matter, and potentially introduce a preferred direction, violating the near isotropy observed on large scales. A wall passing through the observable universe might influence gravitational potentials, lens background light, generate anisotropic expansion, or leave characteristic discontinuities in cosmological fields. Stable networks of sufficiently energetic domain walls are strongly constrained because their density decreases more slowly during expansion than radiation or ordinary matter, allowing them to become cosmologically dominant and spoil the observed smoothness of the universe. This is one reason many viable particle physics models either avoid stable walls, make them decay early, or dilute them through inflation. Yet a boundary associated with a remote bubble collision could be far outside our horizon, while still having produced an ancient perturbation that reached us. So constraints on local wall networks do not automatically remove every cosmological boundary scenario. The crucial scientific task is to derive a signal from a specific field theory and spacetime solution, rather than to label every unexplained feature a scar between realities. A cold region in the microwave sky is not evidence of another universe merely because it looks unusual. The model must predict its shape, scale, polarization, statistical frequency, and relation to other observables before the data are examined. Otherwise, the explanation can be adjusted after every result and lose its power to be tested. Numerical simulations in full general relativity have been used to connect the properties of colliding vacuum bubbles with the perturbations an interior observer might eventually measure, showing how wall dynamics, vacuum structure, and post-collision inflation shape the possible signal. If the hidden separator is a higher dimensional bulk rather than a bubble wall, the search moves from circular patterns in the ancient sky to tiny deviations in gravity and particle behavior. In many brane world models, standard model fields remain confined to the brane, while gravity can explore additional dimensions. At distances much larger than the size or curvature scale of those dimensions, the familiar inverse square force can emerge, but at shorter distances, gravity may strengthen or acquire Yukawa-like corrections as gravitational flux spreads through the extra geometry. Precision torsion balances, microscopic mechanical systems, atomic measurements, and experiments using ultra-cold neutrons have therefore tested whether gravity departs from its established behavior at short range. Current experiments have placed increasingly strong limits on broad classes of extra-dimensional models, but no reproducible deviation has established the presence of a bulk. Particle colliders offer another route because high-energy collisions might produce Kaluza-Klein excitations, missing energy events associated with gravitational modes entering the bulk, or resonances linked to warped geometry, although every such prediction depends on the dimensional scale, coupling strengths, brane thickness, and specific model. Gravitational waves could also carry information if extra polarizations, unusual dispersion, leakage into additional dimensions, or echoes from modified geometry were present. But astrophysical environments create their own complex signatures, and extraordinary interpretations require patterns consistent across many events, rather than a single unexplained irregularity. The quantum branch version of the question is harder to test because decoherence is observable, while the claim that its components are separate worlds belongs partly to interpretation. Experiments can place larger molecules, electrical currents, mechanical resonators, and other systems into increasingly delicate superpositions, then measure how interaction with the environment suppresses interference. These results support the dynamical account of decoherence and the emergence of stable pointer states, but they do not by themselves prove that every decohered component remains as an equally real universe. Several interpretations can agree on the same experimental probabilities, while offering different accounts of what the quantum state represents. Objective collapse models are more directly testable because they modify the dynamics and may predict spontaneous localization, heating, or loss of coherence beyond ordinary environmental effects, whereas conventional unitary interpretations, including Everettian approaches, often differ mainly in ontology rather than laboratory outcomes. Modern reviews still treat the measurement problem as unresolved, and decoherence as an essential mechanism that does not, by itself, select a unique interpretation. This reveals the boundary between observational science and metaphysical completion. A mathematical framework may contain objects called other universes, yet only those features that change measurable probabilities within our causal domain can leave empirical evidence. If another spacetime is completely disconnected from ours, sharing no geometry, field, quantum state, or common origin, then by definition it cannot send us a signal. And no experiment confined to our universe could distinguish its existence from its absence. Such a proposal may remain logically imaginable, but it would not function as an ordinary, testable extension of physics. Models involving bubble collisions, branes, or quantum fields are scientifically richer precisely because they provide some common structure through which traces might arise. The trace may be a temperature modulation, a polarization pattern, an altered gravitational law, a tower of effective particles, a shift in cosmic expansion, or an unexpected loss of quantum coherence. But every possibility must compete with simpler explanations and survive independent observations. For now, the universe has offered no confirmed mark that requires a neighboring cosmos or a physical structure between realities. What we possess instead are limits, increasingly precise maps of where such marks are not, and theories becoming disciplined enough to risk being wrong. That may sound quieter than discovery, but it is how the horizon of knowledge actually advances. Not through declaring that every mystery opens onto another world, but through listening carefully to the oldest light, the weakest gravitational pull, and the faintest surviving interference, asking whether somewhere inside those delicate measurements lies the fading pressure of something our universe once touched. After following the question through geometry, quantum fields, inflation, branes, and the deep architecture of state space, we can finally answer it without hiding behind mystery. What lies between two universes depends entirely on what kind of universes they are, and in the most extreme case, nothing lies between them, because the word between has no physical meaning there. That answer may sound less dramatic than an ocean of darkness or a glowing wall at the edge of creation, yet it is far stranger, because it asks us to abandon one of the oldest habits of the human mind, the belief that every pair of things must be separated by a place. In daily life, separation is always geometric. Two houses have a street between them, two islands have water, two stars have interstellar space, and even two galaxies beyond one another's light are joined by a continuous space-time in which a path can be imagined, whether or not any traveler could survive it. Physics formalizes this intuition through a metric, the structure that assigns intervals between events, and allows us to distinguish time-like, light-like, and space-like relations. If two regions share one metric, then distance can be measured, a midpoint can be defined under suitable conditions, and the question of what occupies the interval becomes legitimate. But if two universes are entirely separate spacetimes, with no common manifold, no shared coordinate chart, no higher dimensional embedding, and no causal or quantum connection, then there is no interval to fill. They are not separated by zero distance, because zero still belongs to a geometry. They are not infinitely far apart, because infinity is still a value inside a system of measurement. Their separation is undefined, not because our rulers are too short, but because no ruler could even be conceptually extended from one to the other. This is the most conservative and logically complete answer for two fully independent universes. There is no vacuum between them, no boundary, no direction pointing across, and no external observer who could see one on the left and the other on the right. Yet that is only one branch of the answer, because cosmologists often use the word universe for structures that are not absolutely independent. If two universes are merely two observable regions within one larger spacetime, then the space between them is ordinary cosmic territory, perhaps forever beyond the horizon of each observer, but still part of one continuous geometry. It may contain galaxies, radiation, dark matter, quantum fields, and the large-scale expansion governed by the same physical laws. Their isolation would be causal rather than ontological. Each region could be unable to receive signals from the other, yet both would still belong to one cosmic whole, just as two ships beyond one another's horizon remain afloat on the same ocean. If the universes are bubbles formed by vacuum decay in an eternally inflating background, then the region between them may be a false vacuum whose energy drives accelerated expansion. In that model, the emptiness between worlds is not passive. It creates more physical volume, stretches the separation between bubble walls, and may continue to nucleate new bubbles while older ones recede beyond causal contact. The universes are not objects floating in pre-existing blackness. They are domains where inflation ended inside a larger field configuration, where inflation continues. What lies between them is therefore a parent state, a high-energy vacuum with geometry, pressure, and dynamics of its own. If two such bubbles collide, the answer can become thinner still. Between their interiors, there may remain a domain wall, a transition layer in which fields move from one vacuum value to another. That wall could possess tension, energy, and gravitational influence. It might accelerate, bend spacetime, release radiation, or separate regions whose particles and forces no longer match. It would not be a border made of matter in the ordinary sense, but a zone where the vacuum itself changes identity. In one direction, atoms may be stable. In the other, the same combinations of fields may not exist at all. The wall would not mark the end of law, but a change in the state through which law becomes physical reality. If the universes are branes, then the answer acquires an extra dimension. Between them could lie a bulk, a higher dimensional spacetime through which gravity or other permitted fields propagate, while ordinary matter remains confined to each brane. The proper distance between the universes would then be measured through the bulk metric, and in a lower dimensional description, that distance might appear as a scalar field, such as the radion. The gap between worlds could influence the strength of gravity, the scale of particle masses, or the evolution of the cosmos, without ever appearing as a visible direction in the sky. Two universes might be separated by only a tiny interval in the hidden dimension, and yet remain completely unreachable to beings made from fields that cannot leave their own brane. If the branes moved, their changing separation could become part of cosmic history, and in speculative ekpyrotic or cyclic models, a collision between them might even be associated with the beginning of a hot expanding phase. None of this is observationally established, but it demonstrates that a real physical something can lie between two universes when a theory supplies a shared higher dimensional structure. If the universes are quantum branches, however, the geometry changes once again. There is no empty corridor between them because they are not located at different addresses in ordinary space. Their distinction lies in the structure of a quantum state, in entanglement, decoherence, and the diminishing overlap of macroscopic records. Two branches may correspond to different histories of the same underlying system, each containing observers who remember a consistent past, while interference between those histories becomes effectively inaccessible. The separation is not measured in miles, but in state-space relations, and what lies between the branches is not a substance at all, only the loss of practical coherence as information spreads into the environment. In an Everettian interpretation, both components may remain within one universal wave function. In other interpretations, the same mathematics may be understood differently. Decoherence is well supported as a physical process, but the claim that every branch is a fully real universe remains interpretive rather than directly observed. If the universes correspond to different vacua in a landscape of fields, then the distance between them may be a geodesic in field space, a barrier in potential energy, or a sequence of allowed transitions through unstable configurations. A tunneling solution may connect one vacuum to another without any object traveling through ordinary space. The path may pass near a saddle point, cross a high-action barrier, or fail to exist within the low-energy theory altogether. In that case, what lies between universes is not a region where someone could wait, but a mathematical route through changing field values, perhaps realized physically only inside a bubble wall or during a quantum transition? These answers seem different because they are different. There is no single universal object called the thing between universes waiting to be discovered. The correct answer belongs to the model, and the model must specify what a universe is, what structure contains or relates the pair, what quantity defines separation, and what evidence could distinguish the proposal from alternatives. At present, no observation has confirmed another universe, a bubble collision, a neighboring brane, or a physical boundary between realities. The cosmic microwave background has not revealed an accepted collision scar. Tests of gravity have not established extra dimensions. Quantum experiments demonstrate superposition and decoherence, but they do not uniquely select a many-worlds ontology. Scientific honesty therefore requires one final layer of silence around the answer. These are disciplined possibilities, not discovered landscapes. Yet the question remains valuable because it exposes the architecture hidden beneath familiar language. It teaches us that emptiness is not nothing, that distance requires geometry, that a boundary can be a field transition rather than an edge, and that two realities can differ without occupying separate places. The deepest conclusion is not that something exotic must sit between universes, but that the existence of a between is itself a physical hypothesis. A shared spacetime may place vacuum there. A higher dimensional theory may place bulk there. A field theory may place a domain wall there. Quantum mechanics may replace spatial separation with decoherence, and two completely independent universes may leave no between at all. So when the night sky appears to open into endless darkness, it may be comforting to remember that darkness is still part of our universe, still shaped by fields, geometry, and time. Beyond a truly separate universe, there would be no darker darkness, no farther shore, and no silent room waiting outside creation. There would simply be no place there to be empty. And perhaps that is the quietest answer physics can offer. Between two universes may lie a vacuum, a wall, a hidden dimension, a path through possibility, or nothing. Not an empty nothing, but the absence of the very relation that would allow the question to begin. So perhaps the deepest answer is not what lies between two universes, but whether between exists at all. As you drift into the quiet, let that thought remain with you. If you enjoyed this journey, please subscribe and share your own answer in the comments below.